Well, let's go ahead and start our review. And we talked about a lot of things this semester, but let's start out with we talked about whether the creation of the planets were all by accident or if there seems to be some kind of order to it, right? And we talked about the idea that there might be forces and things that would that bring about the creation of the planets, right? So if we look at the planets, the ones that are closest to the sun are Mercury and then Venus and then Earth and then Mars and then Jupiter, Saturn, Uranus, Neptune, and Pluto used to be a planet, and now there's talk about bringing it back to make it a planet again. But in essence, we have the four terrestrial planets and the four gas giants. So for the terrestrial planets, we have Mercury, Venus, Mars, Earth, and the Jovian planets, we have Jupiter, Saturn, Neptune, and Uranus in that order. And there's a field called comparative planetology, and in this case, we're going to compare everything to Earth. So, for example, we'll have the Earth being one unit from the sun, and we'll name that the astronomical unit, and that's the distance from the Earth to the sun. And we have an orbital period, and in Earth, it's 1 year, right? 365 days and 24 hours in a day. And we have how the mass of the Earth would be one, and the radius of the Earth would be one, and we have one moon. And the average density of Earth, we'll call it one. So if we look at the terrestrial planets, what we see is that they're the four closest to the sun, so it's about halfway to Earth. Mercury is about halfway to Earth. Venus is about 3/4 of the way, and Mars is about 1.5 times the distance from the sun to the Earth. And we see that as their distance from the sun increases, so does their orbital period, right? So in Earth years, Mercury's Earth is about 1/4 of our years. So every year it circles the sun 4 times when we circle it once. Venus, pretty close to about 0.82, so about 3/4 of a year. And Mars takes about almost 2 of our years to circle to get around the sun. So we see that as we move further away from the Earth, the period increases for the year, or the time it takes to go around the sun once. As for mass, we see that Mercury is pretty small, right? 0.05 times the mass of the Earth. And Venus is getting close to the mass of the Earth. It's about 0.82, and Mars is about 0.11. And if we look at the radius, once again, so they were low masses, right? So if we look at the radius, Mercury is about 0.38, and Venus about 0.95, and Mars about half the radius of the Earth. And if we look at their average densities, right? So for the terrestrial planets, it's about 5,400 kilograms per meter cubed, and 52 and 55, and Mars is a little bit less dense, about 3,900, but they're all pretty close. So in terms of comparing it to Earth's density, Mercury and Venus are really close to being the same density, and Mars is about 3/4 of the density. Then we get out to the gas giants, so Jupiter and Saturn and Uranus and Neptune, and we see that the orbital periods are huge, right? So it takes Saturn about 9 of our years to go around once, and it takes Uranus about 20 years to go around once, and Neptune 30, and I'm sorry, that they're the orbital period. So we have Saturn's about 9 extra astronomical units from the sun, and Uranus is about 20, and Neptune 30, and Pluto about 40. And if we look at their orbital periods, they're about 29 and 84 and 164. And as we move out further from the sun, then the periods get longer. And we talked about this. We said that Kepler looked at this and he found that the square of the period was proportional to the cube of the semi-radius, the semi-major axis. If we look at their masses compared to Earth, Jupiter is like 11 and Saturn's about 10 and Uranus about 4 and Neptune about, I'm sorry, did it again. It was in the wrong column. So Saturn's about 95 and 15 and 15, and Jupiter's huge. It's about 318 times the Earth masses. So we see that they break up into pretty much two groups from their distance to the sun, and the terrestrial ones seem to have a surface that you can walk on, right? Where Jupiter and Saturn and Uranus and Neptune are a little bit different. So we find that there's similar chemistries to Mercury and Venus and Mars, and we said that they're rich in hydrogen and helium are Jupiter and Saturn, and possibly vast quantities of water, as well as hydrogen and helium, are Uranus and Neptune. So here shows a scale drawing of the terrestrial planets, right? So Mercury is the smallest, and then we go to Venus, and then to Earth, and then out to Mars. And in order of size, we have Mercury and Mars and Venus and the Earth. And once again, here we see the distances. So we have the Sun and Mercury and Venus and Earth and Mars. And next comes Jupiter. And if you remember, we said that there were predictions that there should be a planet between Mars and Jupiter, but we don't find one. What we do find is a whole bunch of asteroids. So it's possible that a planet was trying to form there and never made it. All these planets rotate in prograde motion. So what we're saying is that they spin at in the same direction the Earth spins, except for Venus, which spins in the opposite direction. And we said the leading theory for this was that Venus got sideswiped, right? Got hit by something that came through that knocked into it and spun it in the opposite direction. And there was nothing really, no reason for it to start spinning it back in the opposite, in the direction that it was spinning. Note that Earth and Mars both are tilted on their axis, which means that they both have seasons, right? So the reason for our summer is because we're tilted towards the sun during the summer in the northern hemisphere, and the southern hemisphere is tilted away from it. And we said that on the other hand, if, during the winter, the northern hemisphere is tilted away from the sun and the southern hemisphere is tilted towards it. If you remember, we also said that the Earth is closer to the sun in the winter than it is in the summer. Also, if you look at this drawing, what we're trying to, you could see is that all these planets orbit in a plane, like they're not randomly distributed around the sun. So we also talked about their atmospheres a little bit, and we said Mercury didn't have really a detectable atmosphere. It was too hot and too small and too close to the sun. But Venus has a really dense atmosphere, and it makes it unbelievably hot. So the greenhouse effect, which keeps us warm on the Earth, has gone crazy there, and it's just unbelievably hot. So for Mercury, we had large temperature extremes and a really thin atmosphere, and it's unprotected from all these impacts. So one thing is that a lot of things try to hit the Earth, with really small asteroids and things. And what we see is that they burn up in the atmosphere, but they have no atmosphere, right? We also have a nice, strong magnetic field that helps us. So it's continuously, Mercury is continuously bathed in solar radiation, and it has a rough, dark, solid surface. So when we look at Venus, right, that's known as the goddess of beauty, right? And it's nearly the same mass, density, and size of Earth, but it's 30% closer to the sun. So this is important because remember we said we wanted to look for planets that were exoplanets, planets out of our solar system that possibly could support life or that we could live on. And if we notice that even though Venus is the same mass and density, which suggests that there's a lot of things similar to it, and it's similar in size to Earth, but since it's 30% closer to the sun, it's unbelievably hot. So it has a CO2 atmosphere and it's always cloudy, right? And there's large volcanoes, and right, the crust may melt and re-solidify a lot, and no magnetic field. So for these reasons, it's um, it's unlivable, right? So what we want to do when we look for planets is look for something that's similar to the Earth, a similar distance from the sun. We talked about a little bit about the greenhouse effect, and what we said is that our atmosphere doesn't absorb solar radiation. What happens is the ground heats up and then re-radiates out the energy, and that's what warms up the the Earth. And some of the gases in our atmosphere absorb radiation, and that's what keeps the Earth livable. And so it works pretty well here. So on Earth, on Venus, what happens is that there's many more of these gases in the atmosphere, so it became incredibly hot. Right? Don't forget that the Earth has this magnetic field that's tilted away, and the one thing that's good about this magnetic field is that it protects us from harmful particles coming from the sun, right? So if you don't have a magnetic field, what happens is you're constantly bombarded by these high energy charged particles. This also leads to a really beautiful effect on the Earth because what happens is these charged particles get caught in the Earth's magnetic field and they smack into air molecules and they lose energy and give it off as light. And we have the northern lights. Or the auroras, right? So these charged particles get caught in the Earth's magnetic field and cause these. So for Mars, what we said is that it's about half the size of Earth, and a day is about 24 hours, and it's tilted on its axis, so it has seasons like the Earth. And it was always thought that this was the most likely place for human settlement. There's a huge volcano there called Olympus Mons, and it has a cold surface and a thin atmosphere. And there's actually CO2 polar ice caps, so um, like dry ice in essence. And it has two moons, Phobos and Deimos. So if we look at the Jovian planets and we compare them to Earth, what we see is that Jupiter and Saturn are huge. I mean, they can't even be shown in the same picture, right? And Earth and Neptune and um, Uranus and Neptune are still much bigger than the Earth. So interesting things about Jupiter. It has the great red spot, right, and the Galilean moons. And it does have rings like Saturn. And for Saturn, we see the most interesting thing, of course, is the rings. And Uranus is interesting because it's actually tilted and it's spinning in a weird direction that I'll show you a picture of in a second. And in Neptune, there's also storms like Jupiter, right? Because the great red spot is really just a giant hurricane that's been running for a while. So here we see that great red spot. And once again, it's just a huge hurricane that's been there for a while. So for Jupiter, about 1,300 times as big as Earth and about 318 times more massive. So that means that its density is much smaller. It's more than 2 times the mass of all the other planets combined. And people always said they wondered if it would become us, that if it was just a failed star, right? But it's it would need about 75 times more mass to become a star. So it's huge compared to the Earth and compared to all the other planets, but it's small compared to a star. Its atmosphere is mostly hydrogen and helium, so 86% hydrogen and about 13% helium. And it's compressed enormously by the gravity that is pulling things together. So we now know it has more than 16 moons, but Galileo discovered the 4 largest, and they're pretty easy to see with even a small telescope. It has weak rings, so it does have wings like Saturn. In fact, all of them do, but they're not as impressive as Saturn's. It has a strong magnetic field, and there might be a core in there that's terrestrial-like. So it's about 13, but there's about 13 times the Earth um, mass for the core. Jupiter has an atmosphere, and what we see is that it's mostly hydrogen and helium, and then some water ice, and then some ammonia sulfide ice and ammonia ice. So, and it gives it the color and the striations that you see. And of course, this is the great red spot, the storm that's been running on Jupiter. And there's other storms too, but this one's huge, and we can see it from Earth rather easily. So we said it had here are the 4 largest moons: Io, Europa, Ganymede, and Callisto. And once again, when we're looking for places to inhabit or looking for other places that could have life, right? We'd like something that, for instance, has water, right? And is not too hot and not too cold, and see what things look like. So Io is interesting because it has volcanoes on it. It's very close to Jupiter. And so it feels forces pulling on it from Jupiter and also from the other moon. And these 2 forces cause volcanoes to go. For Europa, right, it has no craters and the surface is water ice. And below that we believe is liquid water. So we have water there, but it's pretty cold. So there's ice on the surface. For Ganymede, it's the largest moon. It's larger than Pluto and Mercury combined. So that was one reason for kicking Pluto out of the planet category. So we see tectonic motion going on. So that's what causes some of that. And Callisto is similar to Ganymede, right? And its upper crust may melt and freeze again. You can see like these cracks that are going on. For Saturn, of course, the most interesting thing, or the thing you know more, are the rings, right? So it's about almost 100 times more massive than Earth, and a strong magnetic field, and less compressed than Jupiter. So its density is only about 69 690 kilograms per meter cubed, which means it's less dense than water. It would float in water is what we're saying. And it's tilted by about 27 degrees, and it has many rings, and there's gaps between the rings. So sometimes when we're looking at it in our telescope, we can see it really well, right? So if we're looking at just the right angle, we can see the rings really well, and sometimes not so well. So for instance, from Earth, if we see it tilted like this, we get these nice pictures of the rings. And if it's tilted in these other directions, we can barely see the rings. So what that suggests is that these wings are really wide, but really thin. So these were the planets that we talked about, right? So, and once again, the reason we talked about these is that we were talking about looking for exoplanets, planets that could possibly support life, or possibly that we could colonize if we wanted to, right? Another thing we talked about were stars and the life of death of stars, right? But before that, let's do a quick review of comets and asteroids, right? Because we also talked about them and how important they were. So if we wanted to talk about what we call the vagabonds of the universe, right? And we said that there's like chunks of stuff out there that we kind of think of as debris, right? So there are asteroids and comets and meteoroids. So what we said was that asteroids and meteoroids are just fragments of rocky material. So it could have been a planet that something crashed into, or a planet that never quite formed, things like this. So asteroids are about 100 meters in diameter, right? So think of, so if we make a really rough estimate of a meter being equal to a yard, we're talking something about the size of a football field. And their mass exceeds 10,000 tons. Meteoroids are smaller, okay, and there isn't like a really clear-cut distinction between asteroids and meteoroids. They don't say that if it's bigger than 100, then it's an asteroid. If it's smaller than 100, it's a meteoroid. Comets, on the other hand, are icy rather than rocky, and they run in 1 to 10 kilometers in diameter. So don't forget, 1 kilometer is about 0.6 miles, and 10 kilometers is 6.2 miles. So these small bodies, if you put them all together, they'd still be like a few millionths of the mass of the sun. So these are chunks of rocks and metal left over from the formation of the solar system, right? And we can see that they're big. So some of them are pretty big, right? And I mean, small in comparison to the size of the Earth, but could do some damage, for instance, if they hit the Earth. So most asteroids are less than a kilometer in size and radius, right? So we're talking about 0.6 miles, but there's 4 around that are more than 300 kilometers, right? Ceres, Pallas, Junos, and Vesta. If you remember, we said that there's a predicted planet between Mars and Jupiter, but there's no planet there. But what there is a bunch of this debris. So there's a bunch of asteroids and meteoroids that rotate that are caught trapped in this asteroid belt around the sun, around the sun. And we said that it's possible that maybe this was a planet that never quite got it together. And the reason for this would be the gravitational attraction from the other planets. So it's probably not a destroyed planet and more likely a failed planet. And it's stuck in there due to resonances like the sun's pulling on it, Jupiter's pulling on it, and Jupiter's pretty big. So it can happen. You can see asteroids can be found by looking for moving objects in still pictures. So you can see things coming in from the Earth and see a streak across the sky. So we have a minor planet center that looks at these and sees where they are and sees that there's any danger of them hitting Earth. Right. We also have some that are Earth crossing, so they'll come in and cross in front of the Earth, and sometimes we get nice showers of meteoroids. And so if we look at asteroids being versus meteoroids, they're pretty much the same, just asteroids both have rocky composition, but asteroids are bigger. Some of them are even big enough to have their own moon circulating, rotating around them. So we're talking about meteoroids are usually a few meters in diameter, and most are less than a millimeter. Asteroids are large chunks of rock and metal left over from the formation of the solar systems. And once again, there's no official size between meteoroids and asteroids. You may hear people talk about meteoroid. That's a small rocky object that orbits the sun. A meteor is the streak you see in the sky if one of these happened to cross the Earth's atmosphere and burn up. A meteoroid is any piece of meteoroid or asteroid that makes it to your Earth and hits the Earth and it's made it through the atmosphere. So meteorites are pieces of meteoroids that make it through the Earth without burning up. And here's an example of one. Right? So things hit the Earth every day, and most of the time they simply cause a meteor and burn up in the atmosphere. However, if they do hit, they can make a huge crater, right? So we said we look for things like this. Comets are pretty much dirty snowballs. So they're ice and rock mixed together, right? And they actually, everybody talks about their tail, but they actually have two tails, right? They and both of those tails pretty much point away from the sun. So the tail isn't following the comet exactly. It always points away from the sun. And there's a dust trail and an ion tail that we see. So comets are in the Kuiper belt and the Oort cloud. And here's a picture of what they would look like. So just to continue the review, another thing we talked about were stars. And to do that, we first talked about the sun. So what we see is that the sun is not static, right? If we look at the sun, there's lots going on up there. And here it shows a picture of the sun, and it's our local star, and it's quite average in many ways. However, it's really interesting to study. So he said its radius is about 696,000 kilometers. It's about 2 times 10 to the 30th kilograms with an average density of about 1,400 kilograms per meter cubed. And the surface temperature is nearly 6,000 K. So we talked about the what the sun looks like. So there's an outer layer, the visible surface to the sun that we call the photosphere. There's the chromosphere, which is a layer just above the photosphere, which is kind of like a lower atmosphere. And the corona is kind of like a really hot upper atmosphere. What we see is that the sun kind of has this granule, if we look closely at it, and this granulated appearance. And what this is happening is that there's stuff boiling up from the bottom, and then it cools off and sinks back down. So we get this constant motion, just like if you're boiling water on the stove. We said we could look at this hot atmosphere. A good time to look at it is during an eclipse, right? And we can see this if we block out the rest of the sun, we see this hot atmosphere. So we're talking extremely hot, like millions of Kelvin. And it's kind of the opposite of what you expect. You'd expect as it moves away from the sun, it would get cooler. But this is a very low density, highly ionized gas. And it's moving so fast that it escapes from the sun and becomes the solar wind. And we talked about that hitting the earth and how the earth is protected by its magnetic field. We also said that the sun has the corona. And once again, we could see this during the eclipse. So if we block out the rest of the sun, so it's not so bright, we can see that if the photosphere and the chromosphere are blocked, right? We also note that the sun has these sunspots, right? And these are dark splotches on the surface of the sun, right? And what we see is that that the sun has a magnetic field, and these sunspots were probably caused by these magnetic fields and plasma going around these loops of these suns. So the sun's spinning, and as it's spinning, it causes these kinks to form in the magnetic field, and that's where these come from. We said these sunspots actually affect our climate slightly, and that they have about an 11-year cycle. So every 11 years they reach a maximum, and then they hit a minimum. There's also these things called prominences, which are huge loops of glowing gas that's ejected from the sun, and solar flares that are eruptions from the sun's atmosphere and cause these energetic particles. And we said that what happens is the sun is shining due to nuclear fusion. And what we said is that in essence, 2 hydrogen atoms become a helium atom, in the whole scheme of things, we have 4 hydrogen atoms become 1 helium atom, but 1 helium atom is less massive than the 4 hydrogen atoms, and the lost mass goes into energy. And we said the reason that the sun doesn't collapse on itself is due to this hydrostatic process, this hydrostatic equilibrium, in which case the gravity that's trying to pull in is counteracted by the pressure from how hot it is pushing out. And we said that what happens is that normally these two are equal and opposite. And once the star starts running out of hydrogen in the core, and all that hydrogen is converted to helium, what will happen is that it starts to cool off, and the core contracts and the rest of it expands. So that's where we'll pick up the review on Monday.